By the end of this video, you won't just see XYZ points anymore, you will possess the Python blueprint to turn a raw, chaotic scan into a structured semantic database that actually creates value. So I'm Florent, and this is where we architect the future of spatial innovation. I will not throw, and we are not going to throw, a heavy black box deep learning model at a simple problem just yet. We are going to be smart. Instead, we are combining geometric algorithms, which are fast and precise, with semantic injection. We will use math to find the structure and logic to inject the meaning directly inside of the point cloud. This is important, and I can cite 3 reasons. First, efficiency. You cannot manually segment a city-scale digital twin. We need to inject automation. The second one, accuracy. Algorithms don't get tired. They don't miss a pixel or because they don't get a coffee, for example. And 3, the foundation. You cannot build AI agents or advanced simulation if your data just raw geometry. We really need semantic layers. So if you're ready to build this engine yourself, you're at the right place, and I will show you how. Let's open the hood and look at the Python architecture. Let's build the solution. So this is the input data right now, but I will show you other data sets. So this is a classroom, point cloud, and we visualize it within a Python boilerplate that is available to all the students at the 3D Geodata Academy. So it's full Python. What you see, this little software is full Python. Okay, so the goal is to go and see if we can get segments like this with our approach. A simple approach, super efficient, that can scale to large point cloud as well. So how do we do that? You can see that I have various parameters here, but what we're interested in is how it works. So let me spin off my IDE where I will be coding. And if you are coming from scratch, you don't know Python at all, it's super simple. You spin off your command line, you install Miniconda or Anaconda, and you will take out some packages, some libraries that we will install. NumPy, this is for numerical computation. Matplotlib, this is for plotting. Open3D for 3D stuff. This is included into Python to time and to make sure that we can be efficient at our various stages. And SciPy, this is really a scientific computation library as well, but that is super optimized. And here, you will see that what I show you is what I call vectorized RANSAC and vectorized operation, which is much faster with Python, with some specific programming tricks. All right, so let's me set the console, execute that, and once all of that was installed with pip install NumPy, pip install, and so on, we launch Spider, and we are right there. Okay, so this is done. We can move into the second stage where I define visualization function. And here you have the 3D visualization and 2D visualization. So I just define them. And you can see that I will be using 256 color palette to have for each object, each segment, a specific color. Now let's load the data and profile what we have here. So you see that I have a if-else. If this does not exist, so I cannot find it, we will just fall back to having a random point cloud, which is not ideal, but at least you can run it even if you don't have any data set. But I will make sure that you have access to this one. Okay, so this is the point cloud of the classroom. Super nice. We'll be using that. It will be a nice test bench. Stage 4 is pre-processing. This is where we start getting pretty smart. What I do is I will define a function voxel sample, as you can see here, that will downsample the point cloud using a voxel grid. As we mentioned, we put our little grid, and based on this parameter, we'll return only one specific point from this specific grid of voxel. So if I run that, this is downsampling by keeping 1 point every 5 centimeters, more or less. And you see that it's super gridded like, so it's very structured. This is especially very nice to move into this kind of framework when you have a uniform density. But if you have an ununiform density, something that is heterogeneous, where you have to use where something is more dense or something more sparse, you could push that as a specific features where you compute the density for each neighbor, for example. Now I will just show you, if I put a higher voxel size, you see that you have a much higher sampling part. We could use that as well, but it will be a bit trickier, right, for the table of the chairs. So let's put it to 0.5. That should be enough to have a nice timing. Now what I do, this is stage 5, we'll use a shape recognition algorithm, specifically RANSAC as we mentioned. So we have a number of iterations where we will try to find the plane, and we have a threshold that I push to 3 centimeters to retrieve the plane. So if I use it like this, we retrieve one main plane, that is the ceiling. It's deterministic, so it means that if I were to change the threshold here, maybe I re-execute, yeah, we have still the plane. All right, so now that it works, it looks like it's working, we can move on to using that for all the planar structures and to detect multiple planes. So as you can see, we had the ceiling, but then we have the floor and 3 walls at least. So that means altogether we want to have 5 planes. So this is why I have a max plane, and this is just in the range of max plane. We'll just use the function defined just above. So let me execute that. And yeah, we have 1, 2, 3, 4, and 5 planes. This one is a bit trickier. I think these are considered not outliers, so it deviated a bit the plane, which is okay, which is fine. We can recover from that. So we leave it like this. We could put 6 planes and we'll have the other one, I guess. So let's leave it like this to have something to work on after. We move on to the stage 7, which is object clustering. And what do we do here? Here, we will want to use sparse connectivity between our points and establish some kind of graph-based connectivity structure that will allow us to find connected components of points that looks like they are connected. And this is what I do here. Essentially, I will use I will create my KD tree, right, to know exactly where point falls to be much quicker. And after, I will compute pairs of points based on the epsilon value, and I will query my point cloud using that. And after, I create my matrix, my CSR matrix, that will be able to be leveraged to obtain all my Euclidean clusters. So let me execute for more clarity. Now, you see very clearly that you could establish very nice clusters of points based on this adjacency matrix. And all of them are independent. Even here, this is using the KD tree approach. If we were using a bounding box approach, we would have much more problem. But here, it's pretty cool. If you want to experiment, this is nice. You could put an epsilon value of 0.5 and you will see that we'll get a lot of weird segments, let's say, that are pretty small or not labeled because of the radius search. And this can be optimized based on the sampling of the point cloud that you made. So if you did voxel downsampling at 0.05, if you take 3 times higher, maybe it's a good idea to know exactly how to consider it segment. If you go much bigger, like 55, you may have an issue where you have under segmentation problematics where the groups that you have are much bigger. So it's nice to understand maybe the relationships at several layers, several levels as well, where you could have this multi-layered segmentation approach. Okay, so let's stick with this 15 to have something pretty cool. Do we stop here? No. What we will do is we will combine the planar information of the segments with the cluster segment. So we finalize labels, and after that we project that onto the full-scale point cloud. But before that, let's combine them together. So this is what I do here. It's finished, and now we project that using the KD tree. So essentially, we create a tree based on the sample point cloud, and then we will query this tree by giving him the full point cloud and take the closest neighbors using one workers or all the workers, and this is what we have. This trick is something that is like you could have spent 10 years before finding this specific trick. It's really very niche, but I'm happy to share that with you. Hopefully that will help you a lot in your endeavor with point clouds and so on. So let me close that. You see that we have now the point cloud, and if you want to export, this is how you could write the segment information, and I will do that so that I can show you afterwards something super interesting. So if I'm exporting that like this, this is okay. But what I want to show you is the timing. So if I run now this entire script from scratch, I will leave it to show you this is real time. It spins off the various visualization. I don't put them in the time. So this is the dominant plane. This is the multiplane. This is the clusters. These are the final results. And here the high fidelity segment. I don't time the visualization, so you can see that for the full pipeline here, on this point cloud, which is 1 million point, you have a total time of a little above, it's like 1 second. And it's because I have a lot of process running, and I'm also capturing the video. So you can basically segment 1 million points per second with this approach, so it's already super optimized. And at the end, you have the output, which is here. And what I want to show you is that you visualize it here, right? This is where we want to go after. But I also developed this super nice, let's say, software, which is also 100% Python. And I want to show you the result, for example, here. If I push them there, and let's visualize them, we will have our little classroom point cloud. Beautiful. And what we can do then is look at the segment that is red. And this is often a very big issue with software. This is why I wanted you to have a solution to use that in a Pythonic way, because this is full Python. We can stick with classical open access file format, or we can stick with Python object, which means we never leave the optimized workflow where we don't have writing and reading stuff. And also something then that we do in the course is that we will use this segment information to classify and then to train a model and then to use AI agent and then to automate the complete pipeline. And for that, you have a super cool patent pending. A little trick here is that it's called explosion that I have here, and it allows me to explode my scene as you can see here. Super cool. And then you can label classification or segment you choose. Let's use a segment, and then you can take all that you want, and this will be furniture, this will be furniture, this will be furniture, this will be ground, and then you write the labels, and you have a new field called classification that have your labels. So after that, it's just a matter of exporting and it's done. So this human in the loop is also covered. This is one example, all using Python and boilerplates. So this is just amazing what you can do. So I like to pose some challenges, and if you have time, don't just run the code that I provided yet. Take a data set that you have, a scan of your office or your living room or a construction site maybe, that will be interesting. You run the pipeline, you see where it fails, and you tweak the parameters. Once this is done, you can ask yourself, how can I make this data actionable? And if you don't want to fight your data and you really want to master the complete workflow from classical segmentation all the way to advanced AI implementation, this is where I have designed a specific operating system for this. So just head over to learngeodata.eu to check out if this is the right fit for you. So if you are serious about this, the link is right there under the description. All right, so a fun word, innovation doesn't happen by accident. It really happens by design. I'm super excited, and I will see you in the next video. Bye-bye.